Okay, I'm recording it. So, I'm guessing you want to look at number 3. Is that a
Number
safe
three.
assumption?
Yes, that's a very
Yes.
safe assumption. We literally spent 15 minutes trying to figure out what to do, and then we were like, let's move
Let's move on. Yeah.
on.
Okay. Well, it's a doozy of a problem. I've got a whole page that's basically just setting it up. So,
Oh no.
there are a couple things. Hecht didn't quite finish stating the problem as much as he should have. So, let me switch cameras and show you what I have here. So I even went to the extent of printing out what he wrote and then also printing out the figure that he refers to. This figure here is the one that sort of sets it up. It's two plane waves, one traveling in the x direction and then one traveling in this, not the x direction, the z direction, he labels it, and one traveling in the YZ direction at an angle to Z of theta. And they have the same, we have to assume they have the same frequency and also the same wavelength. That's fairly clear, at least in this diagram. You have the two wavelengths indicated to be the same. So that'll make both Ks the same magnitude, not the same direction, but the same magnitude. Now, what he didn't say, and what you really sort of have to assume, is that the electric field vector, the vector that is sort of the amplitude of the wave out in front. When you write one of these, you write it as an amplitude vector times some sinusoidal or perhaps complex description of it. But that vector out in front, E0, you really have to assume that that's purely in the x direction, that it's purely perpendicular to the paper. If you don't do that, you would end up having to do it for the different components, and the x component would do exactly what the problem is all about, and the other component would do some strange things. And so I just left that out. Lucas, you're back again. I just want to state that the other assumption is that you have to assume that the electric field for both of these waves, the direction of the electric field vector, is perpendicular to the page. So they're both plane polarized, and the electric field is coming out of the page. It's not in the plane of the page. Because if you do that in the plane of the page, you'd have an electric field vector going like this for E1, and then at some angle to that for E2. And then you'd have to get components of that, find the piece of E2 that's also this direction. That would interfere, but they wouldn't be the same amplitude. The other component wouldn't interfere with anything. It would just be there. It would just be sitting in your answer, not having interfered. Anyhow, he apparently doesn't intend that. And in fact, if you look at the section that this figure is borrowed from, it's not about electric fields. It's about scalars. It's just about waves, scalar waves, not vector waves, if you know what I mean. It's not about electric fields. It's like, I don't know, waves of pressure or something like that. He just is using scalar numbers. So if we allow the electric field to be purely in the x direction, then it's sort of irrelevant. Everything's in the x direction. They both just have x components, and they act just like scalars at that point. And so then you can actually do the problem. Okay, I don't know if that's where you were stuck or not, but let's carry on trying to set it up then. So I'm going to try to write these as these two waves. So E1, and again, I'm just going to look at the x component. It's got some amplitude, E0. These two are both supposed to have the same amplitude as well. I don't know if he says that Yeah, he does. That's one thing he does state. Okay. So they both have that amplitude. And then the way you can write this in complex form is just e to the I, and it's k dot r minus omega t. And the two k's, the two k vectors, are different. You've got k1 and k2. K1 points along this z direction, K2 points at some angle to that. So here's where I'm defining these, and I bowed to the wishes of some of you and got rid of IJK and went with XYZ hat because we've already got K's all over the place here. We don't need yet another one, although it's almost as confusing when you have x times x hat and y times y hat and z times z hat. That's the r vector. That's a little bit confusing, not as confusing as having completely different k's. Anyhow, so k1 is just along the z direction. So it's just the magnitude of k times z hat. That magnitude of k is 2 pi over lambda, where lambda is given to us in the problem. Then K2 is a little more complicated since it's at some kind of an angle. It's going to have sine theta and cosine theta in the y and z terms. Neither of them have any x component. K is totally in the plane of the paper, which is y and z in this case. So there's no x component. But I've got the y component being k times sine of theta, so it's 0 if theta is 0. And similarly, if theta is 0, the cosine becomes 1, and you just have k pointing in the z direction. And then as theta changes, you would get the different components of that. Does that all make sense to you? Okay. Then finding k dot r. Well, for R1, K1 dot R is just this KZ dotted with X, X hat, Y, Y hat, Z, Z hat. And that just gets you K times Z. K2 is K sine theta times Y and K cosine theta times Z. So far, so good. Still with me? All right, now we can substitute this expression back in, or these two expressions back into these wave expressions, and you get something like I have here. So kz minus omega t is the first wave traveling just in the z direction. And then the second one has k sine theta y. I should put parentheses in here. That's sine of theta, all of that times y. Cosine, oh, I'm missing it here. Don't even have the theta there. Cosine of theta times z. And I'll even cross my z's. I don't know if some of you do that. I do sometimes. I'm not real consistent about it. You cross a z to make it distinguishable from a 2, I think is the reason. Now, if we add these two together, the E0, and I've also factored out an e to the I omega t. I guess it should be an e to the minus I omega t to be correct. I've just factored that out of the exponential terms, put it out in front. And what's left is this e to the I kz and e to the I plus e to the I k sine theta. Yeah, anyhow, that whole mess. This comment about the bottom, this is just again restating what I said before about the assumption that the electric field is just in the x direction. All right, that's just the beginning. Now we move to page 2. So now what we're going to do is look only at the the xy plane, and that's where z is 0. So if z is 0, then we can take what we had before and eliminate the terms that have z. So right here, e to the I kz, that's just e to the 0 becomes 1. And in this term, the second part in the exponent is gone, and we're left with only the y part. Clear enough? Okay, then the next thing is that you have to realize we're asked for irradiance. And irradiance is the square magnitude of the electric field. So we've got to square this thing, but we're not even just squaring it. Since this is a complex number, we have to multiply it by its complex conjugate to get the proper answer here. We've got to get a real answer. So if you multiply this thing times its complex conjugate, this I omega t, which again should be minus I omega t, that goes away. You multiply that by its complex conjugate, and you get 1. The E0 becomes E0 squared. This part I just wrote out. So here it is again, and then I multiply it by its complex conjugate, which I don't know if you've ever been taught this rule, but it works, that the complex conjugate can be formed by just writing out the very same thing and replacing every I with minus I. You don't have to get it into the usual form of a real plus I times imaginary. You can have it in any form you like and just change all of the I's to, to minus I's, and you get the correct result. So that's what I did here. Now I'm going to do a little bit of fiddling around, and I don't want to keep writing so much, so I defined alpha to be ky sine theta. So this is 1 plus e to the I alpha times 1 plus e to the minus I alpha. And then I FOIL that out. You guys all know the term FOIL?
Yes.
Okay. I never learned that. That's one of the new things that's come up in the last, what, 40 years or something. Getting closer to 50. Foiling that out, that's what I have, collecting the ones together to make a 2, and I'm left with e to the I alpha plus e to the minus I alpha. And then I use Euler's law and realize that the, did I do that right? Yeah, I think I did. Yeah, okay. So the cosines survive, the sines disappear. And so I'm left with 2 cosine of alpha. Pulling a 2 out of this is 1 plus cosine alpha. And that looks a lot like a double angle. Here's where, when I get something like this and I don't want to have 2, I'd rather have 1, especially when you look at the answer and you see, oh, it's got a cosine squared in it. Then I pull down a book that's got all kinds of trig formulas in it. You folks probably, I don't know, way up somewhere up here, you would have just plugged this into something and let it do the work. The only trouble is you have to sort of constrain it. What direction are you trying to go? Some of this is, you're trying to get an answer that looks like what's in the book. I'm not sure how you do that with those programs, but I assume you folks are able to do that. But anyhow, so what I did was looked up in a book and found one of these double angle formulas. So that's what that is. That's just a trigonometric identity getting me from that line to the next one. And now we're most of the way there. Now it's just a matter of simplifying it slightly and then putting back in what I defined alpha to be up here. So that's what this line is, and then further getting rid of k and putting it in terms of lambda, which is what his answer has. And there I am. That wasn't so bad. Keep your wits about you. Oh, no, this is a very hard problem. I don't know, where did you folks get?
Maybe
we
step
were,
one.
yeah, pretty much. And then we were kind of confused about the direction, and like,
Yeah,
we didn't, yeah, at some point we didn't think about that we have to square things to get the radians. We were just done.
yeah, yeah. If you don't do that, you're not going to get anywhere close. And I don't know, if you were dealing with X, well, with Y and Z components of the electric field, that just makes it a horrid mess. You would have to separate it into the different components, and the X component, this is what you get, and the other ones I haven't tried to do. What you should see is, at least if theta is really small, the Y component would behave very similarly. As theta gets large, then the Y component would do something kind of similar, but it wouldn't be complete interference because the two would have different amplitudes. And the Z component would just carry on. There would be no, you only get it from the one wave, so it's just there. Now, the next part of the problem, he asks, where are the zeros? Did you try that? You could have just taken the answer and carried on with that. I don't know if you did that. You didn't, okay. Well, how would we get the zeros for this thing? What would you do? Just look at that expression and see how would you find where the zeros are going to be in the
Well, we would need the term inside the cosine squared to be a multiple of y over 2. Not like a multiple, like
yeah,
an odd.
right, an odd multiple of pi over 2. Or you could say pi over 2 plus n times pi. That's what I did. Yeah, that's what you'd want. To get a 0 in the cosine, that has to be pi over 2 or 3 pi over 2 or 5 pi over 2 or something like that. So I just call that pi over 2 plus n times pi. So that's shown there, where n is any integer. And now you've got pi's everywhere, so you can divide all of those out, and turns into this kind of a formula. So y is going to be lambda over sine theta times n plus a half. Now, say you've got an expression like that. That tells you the y coordinate of any of the zeros. How would you get the separation between them? The distance from one 0 to the next, which should be the same as the distance from one fringe to the next. Yes, Aaron.
Would you set n equal to 1 and then set it equal to 2 and see how far apart they are?
Exactly, yeah. Can you look in the formula and see what the separation is going to be? Is it clear what the delta y would be?
It'd just be lambda over sine theta.
Exactly. You're talking then about a difference of 1 in n, and you have a half in both of them, so that just doesn't do anything. That's sort of like an offset on both of them, and you're interested in the difference from n equals 0 to n equals 1, or n equals 1 to n equals 2, and when you subtract those, this factor of a half is going to disappear. So you're left with just lambda over sine theta. So that's what I've got down here. The separation is just lambda over sine theta. Which means, like many things, if you increase theta, the fringes get closer. That's what's always going to happen in optics when you have larger angles, then the fringe patterns get smaller. Okay, there we go. That was fun. Oh. Okay, where do you want to go next? There's one more I'm pretty sure you're going to want to see, but you'll have to tell me besides that.
Is this one you're talking about is 32?
Yep, 32 is the other one I guessed you would want to see, for sure.
Okay, so yeah, this is the only one, the other ones that we have problems with. So I think we should keep going really fast through all the other problem till we reach 32. Then we spend like half an hour talking about it, and then we keep going.
All right, we can do that.
Just to check our final answers, because the book had wrong final answers for at least 2 of the problems.
Oh, seriously?
Yep, we were so mad at the book.
Okay. Well,
we had a question about number 5 as well.
All right, let's go there. I'll show you.
Well, can we just quickly talk about 4 on the way?
Here's 4. I don't know if you can see all that. This was not done with the intention of showing it like this. Is that readable?
Yes.
Okay.
I think we had a question about 9.4. We were wondering why would the 2 sources not be coherent? Like, is there a specific reason for sure?
Well, if you've got 2 filaments, you're talking about part B?
Yeah.
Yeah, in part B, if you've got 2 filaments, what you're doing then, you're replacing the slit with these 2 filaments. And then what you have is not a single photon that travels through both slits and interferes with itself, or a single wave that travels through and interferes with itself. You have 2 sources. And essentially you could imagine those filaments just sort of emitting random photons any old way, any old time. There's no relation between the 2 of those. So how could you have any interference? They would at times interfere, but at times constructively, at other times destructively. It would be totally random. There's no connection, no correlation between the 2. So that's why there would be no interference. What's interesting is that you still do get it with a light bulb. It doesn't have to be a laser. A light bulb does this. The point I did make, though, is that if you had a single filament illuminating a double slit like this, you will get a kind of interference pattern, but it's a weird one because your light bulb has all different wavelengths. And the different colors create interference patterns that have their fringes separated by different amounts. And what that means is right at the center of the pattern, you'll have a nice white bar because all the colors will agree that's a maximum. But then as you move through successive fringes, you'll start to see a full spectrum. And you can do this, the umbrella trick shows that same effect if you know to look for it. When you look through the fiber of an umbrella and see that slit pattern, that's not the slit pattern, you see an interference pattern. It's 2-dimensional in that case, it's a grid. And looking sort of at the most center spot, you should see that one as white. And then as you look to the side, they spread into colors. That works best if you're looking at an incandescent light, and there aren't very many of those anymore. It's not quite as clear, but anyhow, so you'll get fringes, but they will kind of disperse into colors a little bit.
What is the physics definition of coherence and incoherence in relation to this problem?
Oh boy. Okay. So when you say you've got two sources that are coherent or two waves that are coherent. It means that they have a correlation between each other. So if you know where a peak is on one, you can then figure out where the peak is on the other, something like that, that you have a mathematical relation between the two. Aaron, you've just disappeared, so I don't know whether you're following that, if that's sufficient, or if I should try to say more.
No, that kind of makes sense. I was just checking something in the book because it lists in the back, it says that a bulb at S would produce fringes. We can imagine it as made up of a very large number of incoherent point sources.
Right.
So like why would incoherent point sources create the fringes if they...
Yeah, that's a good way to ask the question. The reason is that the light from each of those incoherent sources goes through both slits. And so the bit of light from one incoherent source is creating that fringe pattern all by itself. And then another little bitty source that's incoherent with that first one is going through both slits and creating, again, that very same pattern. And those all then kind of add in an incoherent way, but they're adding up the same thing. So, yeah.
Okay, thank you.
All right, let's move on quickly. We're going to run out of time here. Number 5. What was this one again?
The main question was, why is it a trough in the middle?
Oh, yes. You just need to play around with audio stuff a little bit to know the answer to that. That's just because somebody crossed the wires. Those two speakers are out of phase. They didn't get them wired up correctly. And that's exactly what you'll get if they're out of phase. For tweeters, it probably doesn't matter. For woofers, it matters hugely. If you get your woofers out of phase, you don't get any bass. You can easily demonstrate that. If you're wondering whether you got your speakers wired up, well, just listen to the bass and try it both ways, and you'll know immediately which way is the right way. And the reason for that is that when you go to lower and lower frequencies, then the pattern that you were looking at, this interference pattern, as you go to low frequencies, that's longer wavelengths, the pattern will spread out. And it'll spread out, and eventually for low enough sounds, that central either maximum or minimum fills the room. And so at low enough frequencies, you either hear nothing or you hear the full bass. It doesn't particularly have these fringes anymore. And so you've got to get it the right way, or you lose all the bass. For the tweeters, it doesn't matter so much. They get all mixed up. But that's a cute little demonstration. If you can all do this in your home sometime if you want. If you've got speakers where you have the wires, some of them don't have wires anymore. They've got plugs of some kind that make sure they're the right way. But if it's got physical wires, and usually they're labeled somehow so that you can keep them the right way, you don't hurt anything. It doesn't harm anything by switching them. Just go ahead and swap them, and you'll immediately hear the difference. At least if you have bass speakers. If they're only the treble, then you won't hear so much difference. So that was the that was the answer that he was after, I think, in sort of the second part of the problem. The other thing I notice is just looking at the whole pattern, it's peaked in the center. There's sort of a general peak, even apart from the fringes, which suggests these speakers are somewhat directional. So they're putting out the sound primarily in this forward direction and not off to the side very much. All right, let's move on. What was next? 11 is what I have next. And I got 0.159 millimeters. And does that agree with anybody? No. Ben didn't get that.
0.119.
Okay.
That was because we, instead of using 4, used 3 because we assumed that it started at 0 and that the fourth bright spot would be at m equals 3 and not m equals 4.
Yeah, okay. Well, that is just a pure matter of semantics. And I would, I read it differently, and I don't really care about this. But if you read in the problem, it says the fourth bright band 1 degree above the central axis. Yeah, what do you count as the, yeah. It's unclear. It's unclear which way. And he doesn't even have answers in the back for this one. So if you called that 3 and got a different answer, fine. Let's not worry about it. Okay, are we now to 32? I think we are. So 32. I did it a much easier way. Hecht has an answer in the back of the book that is a difficult way to do it. Well, it's straightforward to set it up, but the math is kind of hard. But this is what I did. So I took advantage of the fact that he labeled the height of this thing as a over 2. Did that strike you as odd? That sort of suggests right off the bat that maybe that's half of something. And if you sort of reflected the thing down, then you'd have these 2 points being separated by a. And this is very much like an interference from 2 slits, except it's sort of backwards. You've got it coming from the distant source, hitting these 2 points instead of from the 2 points to the distant wall or whatever in the way that we usually do. But the math is the same. And so then it's a matter of tracing these 2 lines back and seeing where is the difference in the path length. And that's the figure I've got down here. Now it's the two paths with A being the distance between these 2 points. And the extra path is this little bit down here. Alpha is the angle, and it's also the angle up in this triangle. A is the hypotenuse, so you can see the extra path is just A sine of alpha. So if that's the extra path length, then the phase difference is just k times that path length. And then I added pi. And that's because there's a phase change when you reflect off the water. That's an extra subtle point here that you have to put in that extra phase change of pi right there. So that gives me a total phase change of Ka sine alpha plus pi. And that gets you there pretty quickly. I'll show you in a minute how Hecht does it. And here's a little description. I don't know if that's helpful or not, but you have to assume that this radio telescope isn't very directional. So that if you had just one source, as that source changed its alpha, you'd get just sort of a very slowly changing intensity. And now if you have 2 sources like this, then you'd get interference between them. So it's going to go up and down like this. And then if we include the phase change on reflection, then at 0 angle, I should put again on here, this is alpha, and over here is I. At a 0 angle of alpha, they would be out of phase. So that's sort of like the speakers. You got that minimum right at the smallest angle. So looking at this, what I want is to get a phase change for the first maximum. I'd want my phase change to be exactly 2 pi. So essentially, we've already got a phase change of pi. We want the rest of this term to make up another factor of pi. So I just said Ka sine alpha plus pi. That's my total phase change. I want that to equal 2 pi. And then you work away a little bit with that, solving for what alpha is. And that's when I get this stuff over here. Were any of you able to get that? Okay. Let me, I'll show you very quickly how Hecht tries to go about it. He does not use that sort of looking at the reflection and seeing the geometry simplified in that way. He sticks with the straightforward way of saying, okay, here's a beam coming in and reflecting off. And if we say as they're coming along, they're in phase right up to this point with each other. Across this dotted line, those two parts should be in phase. And now from there, we've got an R1 on this diagonal line and an R2 on this straight line. And it's the difference between those two that gives rise to the phase shift. And that's just kind of a difficult way to do the problem. So R1 is sine alpha. That's, oh, wait, no, let me say that again. R1 times the sine of alpha is A over 2. Not writing things very clearly here, but that's A over 2. So that's just looking at this little triangle right here. R1 times the sine of alpha is A over 2. And then R2 is R1 times the sine of gamma, gamma being this little angle right there.
Can you, yeah.
Well,
Thanks.
sorry. Well, here's the whole thing. You can, but R2 is R1 times the sine of gamma, gamma being this funny little angle there. That's pi over 2 minus 2 alpha. So I put that in here. Anyhow, it's just a bunch of substituting. Here I solve the first one for R1 and get that expression. R2 is written in terms of R1, so I put that expression into it, and then I furthermore put the definition of gamma into it, and you get this huge mess. Yeah, you can simplify it a little bit, and it's that. And then ultimately, I want to subtract these two to get the difference in the path length. So that's what I'm doing right here, subtracting these two, and I end up with that expression. And that then means that delta, the phase difference, is K times that expression. K times the path difference. And then I've also added the pi in here. And Hecht actually leaves it that way, which seems very strange to me, because you can simplify this. 1 minus cosine of 2 alpha divided by 2 sine of alpha. You might think surely there's a simpler way to express that, and in fact there is. 1 minus cosine of 2 alpha is the same thing as 2 sine squared of alpha. So that whole thing just turns into sine of alpha. So it's, that's where I say that this just seems like an awful mess down here compared to the delta that I had up here was just that. So I like that method much more. But I did this all because I was trying to figure out what in the world was Hecht doing. So yeah, just worked my way through and showed that it is the same. So focus on that part. That's the method I would use, at least. Okay. Shall we move on? $33. I got their answers. Did you all manage to go through a whole bunch of these and come up with their numbers? Okay. I did not do his little suggestion here. You might repeat the calculation for a water film in air. Did anybody do that? I love his language.
This is also completely different than how we did it. We sort of did a logic way through rather than this.
Oh, really?
Yeah, the first step we did the same, but then we were contemplating how to prove it for the next two.
No, I just carried on doing a bunch of reflections and putting them together. Yeah. I mean, the only difference is that oh yeah, these are transmission, and this one is reflection. That's to get the second one. And then in the last one, I have to go through transmission and then 3 reflections and then transmission again. And having done these by now, I know what the numbers are. So I just said 0.8, 0.2, 0.2, 0.2, and 1.2. So that's how I did it. Having done them before, I know that it's 0.8 coming in and 1.2 coming back out again. So that's how I did it. Okay, shall we move on? Getting close to the end of our time anyhow here. What was next? Was it 34? This is a soap film. I haven't looked at this one for quite a while, so I'm not sure.
So
Like that?
we thought it was easy. Yeah.
Yeah,
That
okay.
was
We got the
straightforward.
same number.
Okay. That was 34, and then what's next? 47.
47.
Yeah. That I've got right here. I got 550.
That's what Hecht got as well, but he had a typo. He put in the book, he wrote in the problem that it was 2.35 times 10 to the negative 5, but then in the answer he used 2.53.
And John has the
Oh.
2.53.
I do. Let's see. What was it in the earlier edition? Let's just find out. Chapter 9, that was problem 35 in the old edition. I mean, it doesn't really matter, I guess. You can just see a little bit where the error occurred. Yeah, in the old edition, it's 2.53. I wonder how that happened. Does that mean somebody actually retyped all of these? That's hard to believe. Wow. Okay. They retyped it, but the wrong way. I would have thought they would just copy these over somehow, but
My edition has 2.25, so
okay. Well, anyhow, that's just a simple typo. So, okay, should we move on then? Other than that, we're number 50 is right here. I got 96.7 fringes. You like that? Okay. And then I guess we're on to number 60. And here we go.
So this is also where you have a typo, because in the question it was 500 nanometers.
Oh, for heaven's sakes.
And the N of F was 0.55, not 1.38. So lambda and N are that's the same typo that
Let me
Hecht had.
see. Goodness. Okay, this is number 60.
So it looks like John was using the 1.38 of the coding rather than the 1.5 of the glass.
No, I think there was only one. The coding was like the second problem. But in this problem, we only had one.
Yeah, we weren't given a coding number.
Yeah, we were only given the 1.55.
Yeah, well, that actually is, that's in a sense irrelevant. The 1.55 doesn't matter, but he does say that it's a magnesium fluoride film. And so you're supposed to go to the table and look up the index of refraction of magnesium fluoride. That's where the 1.38 comes
Okay.
from. And the 1.55, as long as it's larger than 1.38, it will reflect. And if you're trying to reduce the reflection, you want those two to interfere. And so you want that optical path length to be a quarter of a wavelength going through the film once. So that's where I do the calculation. But the 500 and 550 is kind of a problem. Yeah, his answer, he uses 550, but in the problem, once again, he's, yeah. Okay.
my book uses it calls it 1.58 instead of 1.55, but it uses that instead of the 1.38.
For their answer.
Correct.
Well, that's just wrong. No, the 1.55, that what you're looking at is the interference between these two reflections, one off of the top of the coating and one off of the interface between the coating and the 1.55 layer. the index of refraction of the 1.55 will affect the intensity of that reflection, but it won't change the phase of it. Well, unless this 1.55 was less than 1.38, then it would have an effect on the phase. But no, that's just wrong. You don't use the what you use is the 1.38 that your little reflected beam is going through that film. It's the index of that film that matters, not the index of the substrate. Yeah, so well, we're picking up several errors here. Couple of typos in there, and you've got an actual incorrect calculation there. So yeah. All right. Well, I'm going to let you go in just a couple minutes here. Just to say a word that in the next chapter, we're going to get into great fun dealing with these phasor diagrams. That is the whole game when you get into chapter 10, doing it over and over and over again. So you'll have to get used to that when you're considering different beams. Just to look at one example. So here is the pattern that you get from a single slit. You get a large central maximum, and then you get these funny little side fringes. And one way of looking at that is thinking about the electric field that that comes from the light that has taken different paths through this. And if you look at a diagram like this one, oh, that's doing funny things on my screen. Is it on yours? Okay. If you make
Doing
it full
funny
screen,
things.
maybe not so much. I don't know.
It was
It's still an
moving.
issue in full screen.
Oh, is it? Okay. Well,
Are we assuming they are straight lines?
they are. They are straight lines, and they don't have. That's we're seeing moire fringes. It's sometimes called interference. As I move the book, you see those lines going through, I imagine. Yeah. All right. Well, that's not what this lesson is supposed to be about, but what you're going to be doing is at some very distant point where this all hits a wall, that on this scale is going to be like miles away. You're going to be considering the electric field of these different contributions, these different pieces, these different bits of the wave. And what you do is you think about the phase of those different ones. You assume they're all the same amplitude, at least initially. Later on, we even change the amplitude. But the question is about the phase. Now, if they're all going straight like this, the path length is the same for all of them, and so there's no phase change. And so when you add up those contributions, you'd be putting together these phasors, these little arrows, all pointing the same way. They all have the same phase. So they're all pointing in phase space. They're all pointing the same direction. Doesn't really matter what direction it is. You usually make it horizontal, but you wouldn't have to. But now if you look down here, if you're off at some angle, then you're going to have a little bit of a wavelength shift for some of these. They're not going to be the same. And what that results in is all these interesting diagrams on this page. Here's what I just talked about. Add up a whole bunch of different arrows. And then what happens if you're off at some angle? Well, then each of the arrows is a little different angle from the next arrow. And so you end up with a chain of these things that looks something like that. And the final intensity is the sum of these things. And so you end up with some intensity that's that length instead of that length. Now, what we've done so far is a bunch of discrete arrows, but in fact, in this case, it's continuous because this is just a single slit, and it's really got an infinite number of little pieces of the wave in there. And so instead of having a chain of little arrows like this, it's really a nice little circle like so. That's the ultimate answer. And now as you change the angle that you're looking at, that changes how much there's a phase difference from one arrow to the next. And it changes ultimately how quickly this thing curls, if you like. And that's where you get pictures that look like this. And maybe if you're off at a large angle, this thing loops around several times. And if you pick just the right angle, it loops around a couple times and comes right back to 0. That would be a particular angle at which there would be a null in the pattern. So that's the kind of thing. I hope you can read this and make sense of it. I'll probably talk some more about this kind of thing during our regular class time tomorrow at 2. See if we can go over some of this and make sense out of it. But that's the meat of it, is doing these phasor diagrams and making sense of all these different situations. So that's the end of today. I'll see you again tomorrow, I guess, at 2 o'clock. Does that suit everybody?
Do we have a
Okay.
quiz?
Very good. That's all for today.
Do
So we don't have a
quiz tomorrow?
quiz?
Oh, I didn't make one. I'm sorry. I didn't make a quiz today. I should have. Shucks. Doggone it. Maybe I'll give you one tomorrow. Yeah, maybe I'll give you one tomorrow. I didn't think about it today, so we'll do it tomorrow. All right.
I'm heading off to my next meeting.
Okay. Bye-bye.
Bye.